Hi everybody. This is the first part of our lecture on Chapter 1, which is on propositional logic. Okay, so to start off with, a proposition or sometimes it's called a statement, is a sentence or part of a sentence that can stand on its own as a sentence, that has a definite truth value. Definite truth value, either true or false. All right, so for example, one, the door is open. The door is open in my office and there's a lot of noise, so I'm going to go close it. So the door is open, that could be a true or a false statement, depending on which door you're referring to, but, it's true or false. Either it's closed and latched, or it's not. 2, 4 is even. All right, this is true. And this is true depending on which door we're talking about. Four is even. That's true. 11 is prime. All right, that's true. 9 is prime. All right, that's false. All right, so all of these statements, right? Each one of these is a sentence, or it could be a sentence within a sentence, right? So a statement is always a sentence or a fragment of a sentence that can stand on its own as a sentence, right? I mean, you can always get sentences within sentences. So it's something that stands on its own as a sentence that has a definite truth value. Non-examples. 1, Mark is tall. All right, this is a value judgment. Right, so it doesn't have a well-defined truth value. Right, I mean, it depends on the context. I mean, if Mark is the tallest person in his family, folks might say in his family that he is tall. If Mark is 5'6", like me, then most people would say he's not. 1 more. 2, do you like chocolate? Right, I mean, this is a question, which doesn't have a truth value. 3, Barney, horse. What's wrong with this? Why is this not proposition? Why is this not a statement? Right? What's one of the qualifications that a statement or a proposition is supposed to have is that it's a sentence. This is not a sentence. It has no verb. Right? A proposition is always a sentence. And at the very least, a sentence has a subject, a verb, and a predicate. Right? Subject, verb, and I guess predicate is one thing. It's kind of a loaded word in logic, but subject, verb, and a predicate. So Mark is tall. Mark runs fast. Mark, has black hair, whatever it might be. All right. Logical connectors. So propositions can be connected together to yield larger. Larger, not that really has necessarily much of a meaning, but to yield, more complicated, to yield compound propositions. So the first connector that we're going to talk about is conjunction. So conjunction is symbolized by this and means in the English language. No, let me see. Let's do it this way. So if A and B are both propositions, then a conjunction B in the English language conjunction often reads as, which often reads as A and B, or it could read as A, comma, furthermore, B, or it could be A but B. That's also conjunction when you say but. It just means and, right? How does but mean and? It's a conjunction, but it signifies something a little bit more in the English language. It's something sort of unexpected or some sort of contrast, right? Like, the sky is cloudy, but it's not raining. What does that mean? That means the sky is cloudy and it's not raining. Right? But the but somehow signifies that it's unexpected. It gives some sort of prosaic flair. But from a strictly logical point of view, it's just conjunction. What else? A also, B. And there's others. Okay, the truth value of a conjunction B is shown in the following table. So, oops, we've got these two propositions, A and B, and each one of A and B could be either true or false. Well, in order to get all possible combinations, right, we write it like this. For A, we write true, true, false, false, and then for B, true, false, true, false. Right? That gives us all possible combinations of truth values for A and B together. Right? There's two possibilities for A, two possibilities for B. So together there are 2 times 2, which is 4 possibilities for A and B. And then the conjunction A and B is true when A and B are both true. And then it's false otherwise. If either A is false or B is false, then A and B is false. Okay? Conjunction can also, that's conjunction with two propositions. All right, you take two propositions and make the conjunction of them. You have A, you have B, and then you have the proposition A and B. And the truth values given the truth value of the conjunction, given the truth values of A and B, are as shown. But conjunction can also be used to connect 3 or more propositions. Right? A1 conjunction, A2 conjunction, A3 or AN is true when each AI is true on its own. It is false when any one of the AIs is false, any one or more. So, for example, if I said, right, the sky is blue and the trees are green, and the sky is blue and the leaves are green and the clouds are white and the pavement is black and the frog is purple. Right? That's false. Okay? Even though all of these things I said before, the sky is blue, the clouds are white, the pavement is black, the leaves are green, even though each one of those things is true, the frog is purple is false. Right? So when you put the frog is purple in conjunction with whatever else, it just makes it false. Okay? More about, the English language and using propositional logic is later to come. So that's conjunction. The second connector is called disjunction. And disjunction, so let me write it in exactly the same way I wrote it here. So disjunction if A and B are propositions, then A disjunction B is the disjunction of A and B. In the English language, disjunction often reads as A or B. And that's usually the way it goes. I mean, I don't know too many other words that go for the disjunction. A or B, or sometimes we say either A or B. Oops. Or we could say one of A and B. One of A and B is true, something like that. So these are words for disjunction. And the truth value for the disjunction is as shown in this table, not that one, but the new one I'm going to write. So the truth value for A disjunction B, given the truth values for A and B, is shown in the following table. So it means or. Now, what do we mean by or in the English language? All right, so again, these are the four combinations of truth values for A and B together. There's two choices for A, two choices for B, so 2 times 2 give you 4 choices. And A disjunction B is true when A is true and B is false, when B is true and A is false, or when A and B is both true. It's only false when they're both false. Okay, and that's usually what we mean by or in the English language. Now, sometimes when you use the word or, well, you say, well, either you're going to have this or you're going to have that, but you're not going to have both. Okay, that's usually less common. Okay, and it's kind of ambiguous, actually. I mean, normally we'll say, if it's ambiguous and the ambiguity causes a problem, normally we'd say, if we mean the exclusive or, either you have this or you have this, but this or you have that, but you don't have both. All right, normally we'll say that. Okay, or we could say like you're gonna have this or you're gonna have that, or maybe both. All right, so in the English language, or does have that sort of ambiguity. There's the ordinary or and there's the exclusive or. Okay, but in propositional logic, we have to have a definite meaning, and it's the ordinary or. It's not the exclusive or. Okay, so it's true when either one of A or B is true. Disjunction can also be used to connect 3 or more propositions together, just like conjunction can. Can be used to connect 3 or more propositions together. So A1 disjunction A2 disjunction AN is true when any one or more AIs any one or more of the AIs. Oh boy, let's just. Ugh. It's true when any one or more of the AIs is true on its own. It's false only when each AI is false on its own. Right, so I mean, if I was to say, right, something like this, so my coffee mug has gasoline in it, or my table is not flat, or my walls, I guess you can't say, it's hard to, it's easier when people are in the room with me. If I was to say 2 is odd, or 3 is even, or 9 is prime, all these things are false, right? Or what? Or circles have corners, or squares have 4 sides, right? So I mean, all the things I said at the beginning, those things were all false. But because squares have 4 sides, the whole statement is true. All I need is just one of those things is true. It could be that all of them are true, right? Squares have 4 sides, or 3 is prime, or 4 is even. If I said that, that's true. Even though all the things are true, the disjunction of them is still true. All you need is that one of them is true on its own. One or more. And one or more means exactly that. One or more. Doesn't mean there's an upper limit. Doesn't mean all. Doesn't mean not all. Just one or more. All right. So that's conjunction and disjunction. Number 3 connector is implication. So, and this is by far the most complicated. Given 2 propositions, A and B, the implication A implies B is a statement which can mean the following, any of the, in the English language. A implies B. If A, then B. B when A. Now, there's a lot of these things in English for implication. You can say it in all kinds of different ways. The best way is A implies B, if A, then B. All these other ones can really get confusing. This one has the A first, then the B. This has the A first, then the B. This one switches them around. B when A. Anyway, how do you know? I mean, how do you know which implications these are? We'll talk more about that. Okay, but just let me put a few more up here. B follows from A. B if A. B is necessary for A. A is sufficient for B, and more. Again, we'll talk about, what these all have in common and how you can really see it in a nice way. Okay, so you have A implies B, if A then B, B when A, B follows from A, B if A, B is necessary for A is sufficient for B, and more. The truth value for A implies B is as follows. Oh, so let me say it right now. Essentially, A implies B describes a containment relation. So instances where A is true. So this circle represents instances where A is true. And this circle, oval, represents instances where B is true. All right, describes a containment relation, instances where A is true are contained in instances where B is true. If A is true, then B is true. If you've got something inside A, then that something is inside B. If you've got something, B is necessary for A. B is necessary for A because whenever you fall inside A, you also fall inside B. You've got B if you're inside A. You're inside B if you're inside A. See how they're all? Let's go through them one by one. So A implies B. If you got an A, it implies you got a B because A is contained in B. If you got an A, then you got a B because A is contained in B. You've got B whenever you got A. You got to have B whenever you have A because something that's an A is also a B. B follows from A because the A's are contained in the B. You've got B if you've got A. B is necessary for A because everything that's inside A is inside of B. So B is necessary for A. A is sufficient for B. If you would like to have a B, you might as well get an A. It suffices to have an A because the A's are all B's. Right? If you want a rectangle, it suffices to have a square. The squares are rectangles. Not all rectangles are squares. Right? This kind of thing. And more. There's other ones, but these are the least annoying of them. But they all mean this containment relationship. Now, the truth value of A implies B is given in the following table. So let me copy that table from upstairs. Copy and paste. All right. So when A is true and B is true, this is true. When A is true and B is false, the implication is false. And then when A is false, doesn't matter what's going on with B, the implication is true. So, by the way, note but terminology. Whenever you have an implication, A implies B. So A is called the hypothesis. A is called the hypothesis. B is called the conclusion. All right, one more try. There we go. A is called the hypothesis, B is the conclusion. So basically, an implication is true if the truth of the hypothesis implies the truth of the conclusion. Right? The only time it's false is if the hypothesis is true and the conclusion is false. These are important. If the hypothesis is false, the implication is true. This is the implication. If the hypothesis is false, the implication is true. The conclusion is irrelevant. Let me say it again. If the hypothesis is false, the implication is true. If the hypothesis is false, the implication is true. The conclusion is irrelevant. Okay, that's a convention of propositional logic. In the English language, it's a little bit sort of obscure or a little bit, ambiguous, right? I mean, if I said to you, like I said to my kids, if I said to my kids, well, if you eat your dinner, then, we can have dessert. If you eat your dinner, then you can have your dessert. Right? So if they ate their dinner and then I gave them dessert, that means I didn't lie to them. Or I kept my promise, right? If they ate their dinner but I didn't give them dessert, then I didn't keep my promise. I lied to them. If they didn't eat their dinner but I gave them the ice cream anyway, well, did I lie? Well, I didn't say what happened if you don't eat your dinner. If you eat your dinner, in other words, we're saying the hypothesis is true. If you eat the dinner, then you can have dessert. All right, and if you didn't have dessert, then that means I lied to you when you ate your dinner. I didn't say anything about when you don't eat your dinner. If you didn't eat your dinner, then I gave you the dessert anyway. I still didn't lie. Or if you didn't eat your dinner and I didn't give you the dessert, then I still didn't lie. So no, that's a matter of convention, really. But there's good reasons for that convention, and we'll talk more about it later. You'll see why, and I'm sure you'll agree that's the right convention. Okay, so that's number 3. Number 4, logical equivalence. So let me say it the same way. Yeah. Given two propositions A and B, the equivalence, or sometimes it's called double implication, A is equivalent to B, can be read in the English language A if and only if B. A if and only if B. Or A is equivalent to B. Or A is necessary and sufficient for B. Those are pretty much the only 3 that you get. And then the truth value is as follows. So logical equivalence means like equality in the logical sense. Both true, double implication is true. Both false, double implication is true. One true, the other false, double implication is false. Right? So it's equality of logical value. Both true or both false. Then we're true. One is true, the other is false, then the double implication is false. And then the last one is it's called a connector, but it's not really a connector because it only uses one proposition, and that's called negation. So given a proposition A, A not means not A. And the logical value is as follows. So you have one proposition A, which is either true or false, and then A naught has exactly the opposite truth value. False and then true. All right, how long have we been going now? All right, let's do just a few more minutes. Operator precedence. So, like ordinary arithmetic, so what are logical connectors? So logical connectors, they're like arithmetic of logical values, right? So addition, subtraction, multiplication, and division, and exponentiation, these are arithmetic of numbers, of real numbers. These are like an arithmetic of logical values. It's often called Boolean arithmetic. So like in ordinary arithmetic, like multiplication takes precedence over addition. Here we also have operator precedence. So operator precedence, the one that has the highest precedence is negation. The next highest precedence are and or, conjunction and disjunction, and neither one has precedence over the other. The third one is implication, and the fourth one is double implication. So A disjunction B implies C means that the disjunction came first rather than the disjunction of A with the implication B implies C. Right? So a logical connector, it always takes two statements to put them together. So when I write this here, the implication has lower precedence than the disjunction. The disjunction must be evaluated first. So first we evaluate the disjunction. And then we evaluate the implication of A or B with C. Okay? If you mean this, right, first we're going to do the implication of B and C, and then take the disjunction with A, right? That's different. And in that case, you have to have the parentheses. Right? So for the latter statement, parentheses are necessary. So for example, another example, if I wrote this, A or B and C is ambiguous because neither disjunction or conjunction has precedence over the other. Okay, we must write to see which operation comes first. Either the disjunction, A or B, and then taking the conjunction with C, or the conjunction of B and C, and then taking the disjunction with A. All right. So now, a truth table so given a compound statement, in propositional logic, so something that uses a bunch of connectors. A truth table displays the truth value of that statement for all possible combinations of truth values of the small propositions it is constructed from. Or maybe we'll just say bare. So, for example, so complete the truth table for the statement. So we'll say A or B. Conjunction. A or C naught. Conjunction. C. Logically equivalent to C. So I have this statement, and I want to write the truth table for it. First of all, how many bare propositions are there? There's 3. There's A, there's B, and there's C. So 3 bare propositions needs 2 to the 3 equals 8 rows, because the statement has 3, is built from 3 propositions. A, B, and C. Okay, so we're going to need 8 rows here. So 1, 2, 3, 4, 5, 6, 7, 8. And we start with the bare propositions themselves, A, B, and C. And we need to show all possible truth combinations of A, B, and C. And there's 8 of them. Well, how do you get all 8 of them? Well, here's one way to do it. So A is either true or false. So you write down 4 trues, 4 false. So 4 and then 4. For the B, you go 2 at a time. True, true, false, false. True, true, false, false. And then for C, 1 at a time. True, false, true, false, true, false, true, false. And this will give you all 8 combinations. False, 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 true, false. You know, this might remind you of the binary numbers from 0 to 7. Because that's what they are, actually. Right, so this is 0, 1, 2, 3, 4, 5, 6, 7. So, thinking of f as 0 and t as 1, these are all binary numbers from 0 to 7. If you don't know about that binary arithmetic, maybe we'll talk about that later. But it's not something you need to worry about right now. So at any rate, this is one way to do it: 4 trues, 4 false, 2 trues, 2 false, 2 true, 2 false, and then 1, 1, 1, 1, 1, 1, and 1. All right. So what operations come first? Well, inside the parentheses we have this disjunction, A or B. And then we also have this negation here. The C is negated. So we're going to need to know, and that comes first. Negation is the highest precedence. So we're going to need to know what the negation of C is. So let's just write that down. All right. Now I have the conjunction A with B, or disjunction, sorry. The disjunction of A and B is false only when both A and B are false. Don't think I can get it all in the screen. There we go. So the disjunction of A and B is false in rows 7 and 8. It's true otherwise because one of A or B is true in the first 6 rows. Right? In these 6 rows, one of A and B is true, so A or B is true, and in the last 2 it's false. And then the disjunction of A and C, or A and C naught, right? The negation comes first, then the disjunction. Okay, that's false when A is false and C naught is false. So where's that happen? That happens here, and it happens here. Right? A is false, C naught is false, A is false, C naught is false, and then in every other row, either A is false or C naught is true. And then I want the conjunction, right? This conjunction comes next. Conjunction takes precedence over double implication. Double implication, or logical equivalence, that's got the lowest precedence of all. So this conjunction comes next. So I'm taking the conjunction of C and this and this. And that's true when each is true on its own. So A or B and A or C naught and C. Okay, so all 3 need to be true. Does that happen anywhere? Right here, true, true, true. So it's true there. C is false. True, true, true. It's true here. C is false. True, true, false. False. True, false, false. And then false. So true, false, 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 false. And then the last entire statement, we have A or B and A or C naught and C if and only if C. So that's true when they have the same truth value. So they're both true here. They're both false here. In row 3, C is false. No, C is true and this is true. Yeah. Let me double check. So they're row 1, they're both true. In row 2, they're both false. In row 3, they're both true. In row 4, they're both false. So the double implication is true. In row 5, one is true and the other is false. In row 6, they're both false. So that's true. In row 7, one is true and one is false. And then in row 8, they're both false. So true, 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 false, true, false, true. So that's the final column, and that is the truth value of this entire propositional logic statement, given the 8 combinations of truth values for A, B, and C. So when A is true, B is true, and C is false, this statement is true. All right, when A is false, B is false, and C is true, this statement is false. All right, so that's the truth table for this. Okay, so I'll leave it at that for the first part of our lecture on this section. We will continue the section in a later lecture.